All right. So then, meanwhile, all right, how are things going for you? Good. Life is good?
Yep. Can't complain. It's good.
Can't complain? What do you mean by you can't complain? As in like things are perfect or things are reasonably okay or what?
Reasonably okay.
Here's the next one of problems.
Okay.
And the quiz is on the next week, a week from now.
Yeah, next Thursday.
Yeah, so quiz is next Thursday?
Yeah, the
next
17th, I think.
Yeah, so that gives you some time. I think I'll tell you where to cut, whether your cutoff point is, which is not that much, right? And then we'll just wrap up today, and then we actually go to the gas chromatography chapter.
I have one quick question. Do you have time to do like one homework problem that I have a question on, or would
We
you?
might, or actually,
I mean, I can meet you after class or out of class sometime.
yeah, maybe after class because
Okay.
yeah, and that way Megan doesn't get confused.
It's just a quick one, yeah. Just what equation?
In fact, yeah. You ask a question and then after class and then you go back. You know, if it's a theoretical issue, so I'll answer it and then you go back and do it.
Mm-hmm.
And if it's just a numbering issue, I mean,
Yeah.
plug it in, then I'll show you how to do it first. Well, sort of like I'll show you how to go about it first. Yeah, sounds good, right? So where are we? Let's see. We have, let's see, I think I said resolution, I think. H is small for efficient column or something like that.
Ended
Yes.
with, yeah.
Yes. So I think we are going with resolution. Right, resolution, right? So basically, what is resolution, right? The resolution is degree of separation. Right, of two peaks. Right, so mathematically speaking, right, resolution is defined as, well, two peaks. So you have, relative distance. So you have T retention time, right, of the second retention, right, minus PR of the first retention over 0.5. That width of 2 plus the width of the first one, right? Whereas when you look at it, if you have two peaks, let's say if you have two peaks. By the way, keep that in mind. I put T prime and TR right here, but actually this could very well be the same thing as TR2 minus TR1, right? The reason is because, all right, so you have the width of the 1 and the width of 2, right? And then as time passes, right? So you have retention time. So here you have the retention time of 1 and then retention time 2, right? Now keep that in mind. What you're really looking at is, is delta TR, right? So whether you use adjusted retention time or just the retention time, it makes no difference because you're really looking at here is just delta TR anyways. Because it's relative to your peak here, TM anyway. So I mean, you're only looking at this this distance minus this distance or this distance minus this distance. You're still looking at delta TR anyway. So keep that in mind. Right? So meaning that, even if you don't know the TM is, doesn't really matter, okay, right? Now, that said, right? Now, let's see. So this is the definition. So I'll call it equation 1. Right? Equation 1, right? Now, so equation 1, all right? And let's see, combining combining equation 1 and not yesterday, but Thursday's equation, n is equal to 16 detention time of days, right? This is just general equation, but for each one, basically, so you are substituting, right? Then resolution is equal to, well, I mean, TR2, right, minus TR1, right, over 4 TR2 times 10 to the 1 half, right, is equal to, well, let's square root of 10 over 4, 1 minus PR1 over PR2. Again, okay. For the sake of simplicity, I'm just not putting prime here, but the same thing. And because I noticed that your book actually doesn't use the prime for these, but it's at the end they're the same thing because it's relative to t. Anyways, for resolution. So now this is equation 2, right? So then underneath here, right, using partition coefficient, right, this equation 2 becomes, I'm just deriving the resolution equation basically, right, in terms of the k prime and alpha. That's all I'm doing. So resolution is equal to 1 to the half over 4. I'm just square root showing this way. 1 minus 1 plus k prime 1 over 1 plus k2 prime, right? This is equal to 1 half over 4. And then, well, we need 1 minus, so you can just take a common denominator. You can get k2 prime minus k1 prime over 1 plus k2 prime, right? And this is equation 3, right? Now, and if you combine this equation 3, combining equation 3, right, and the definition of alpha, right, gives, well, by the way, assuming k1 prime is about the same as k2 prime, right? It's about the same as k prime, meaning the efficiency is about the same. Then RS is equal to 1/4 alpha minus 1 over alpha k prime over 1 plus k prime times L over H to 1 half. Yeah. Okay, so what does this mean? Well, what do we care, right? Basically, this is, you're showing, you're seeing the resolution in terms of the alpha and k prime, basically, right? The k prime, all right?
No, I was just, because in the book it has KD prime, but
KD?
you're
K,
assuming that they're all about
yeah,
equal, so it doesn't matter.
Right, yeah. Right? So, yeah, they're about the same.
Mhm.
Yeah. And basically, what it means is that the resolution is a function of selectivity factor, all right, or partition coefficient, all right? Oh, makes sense, right? So now, what does it mean? All right. So now, can I erase this?
Yeah, go for it.
And be sure to take good notes, as in like at least, what I write on the board, so they can copy. In case that video is not, like, the resolution isn't high enough. In fact, I'm gonna check a little bit. Well, actually, it's already still video here. I can see the red, which means it's a good sign. All right. So, I'm gonna put this up on Sakai.
Okay.
Wait, let's see. No, they're not equipped to handle that much video, so let's see. I'll probably have to put it on YouTube. All right. Worst case scenario, I'll put it on the media server on WNJ. I think if the bandwidth is restricted for YouTube, which WNJ does, then you may have to hit pause, and then you have to wait. But depending on the file size, it may actually take time to upload. Last time it took like 8 hours. So. But yeah, that was. I mean, I put up maybe it was like 8 hours, but I had like 4 videos queued. So.
Oh really?
Yeah, but still, it took like 2 hours on each. So they restrict the bandwidth. So. Anyway, so what does it mean? Well, this is what it means. The function of an alpha and k prime. So now, this is what it means. Couple of things. 3, right? So, for column, let's see. The selectivity factor. Let's see. Let's make a pictorial representation. It's much easier. So here we go. So let's say you have, let's say, 2 things. Like say 2 peaks, like that, right? And drawing lines. Let's draw it first. So both peaks, retention time is the same, right? But obviously one is more desirable in terms of chromatography peaks, right? And you've seen both. I mean, if you remember from your calculation lab and HPLC, some peaks came out really nice and tight, and some, towards the end it kind of was broad, right? In GC. Did you guys do GC in this?
Yeah.
Okay. All right. So, and did you guys have to fiddle with the temperature programming for GCMS? Do you guys remember? What do you remember?
We looked at cocaine.
Okay.
But I don't.
You don't.
I mean, we didn't.
Right.
We just gave the sample to
right.
Fokker Lowy and Sharon.
Okay. Well, I think I have a copy. In fact, I'm gonna talk about it in a minute. But now, let's see. But so let's say you have 2 peaks. All right. Let's say injection happens somewhere around, I don't know. Here's the injection, All right. So now, basically, what happens is, in this case, all right, you have adequate selectivity, meaning it can resolve these 2, right, peaks, right, adequate selectivity, right, but poor efficiency, right. Now, but you can actually increase. I mean, you can increase alpha. I mean, if you remember, if you look at the equation earlier, right? If you look at the equation earlier, I mean, if you it's alpha minus 1 over alpha, right? So, but if you increase alpha, right, it increases. Well, resolution will become better. In this case, actually, yeah, resolution becomes better. But now, increasing alpha makes a good efficiency, right? And selectivity, right? By the way, efficiency means how narrow the bands are, or base width. Right? So now, all right, So now, so keep that in mind. Now going back to the equation, right? Again, just to remind you, you don't have to. Well, if you want to write this on the fine. Let me just rewrite it as a note for myself. And that's 1 over alpha, right? Times k prime over plus k prime. All right. So again, now, so you can change other things, k, but again, k depends on retention time. Also, depending on the length of the column, all right? And also theoretical plate height, all right? So now, so what does it mean? So resolution actually depends on 3 things, all right? Well, I mean, well, number one, depends on, so resolution depends on 3 things, all right? So here, RS depends on primarily 3 things. Number one, well, I mean, column, here this part is a column, right? Column length, right? Right, because the column length or theoretical plate height, right? So column, right? All right. And 2, right? The rate of migration. Right? Or capacity factor. That varies with k prime, right? And also the efficiency factor that depends on L over H. This is the theoretical plate number. Right? So keep that in mind. Now, and so again, retention time, if 2 peaks, these are very well resolved, right? Then a higher efficiency because each peak, the base is narrower and they are far apart. Now, sometimes you do get peaks. You don't have to write this one, but if you have injection point, I mean, you do get something like this too. All right? I mean, it's still resolved, right? But in this case, efficiency is not that great. So well, efficiency is good because base height, so base width is narrow, right? But the selectivity is, yeah, it's good, but it's marginal because they are next to each other. So keep that in mind, right? So well, just to make a note, if you want to write this one, you can write one too. But here, this case, it's a good efficiency because peak is high, right? But I wouldn't call it poor, but reasonable selectivity. I mean, not great because they're too close to each other. And for this case, because of low k prime, right? I mean, k prime is a function of retention time, so in reality, if two things, let's see, well, yeah, so I think it's optimal range underneath here, right? The optimal range, right? Optimal range, right, for K is about 2. So when you actually do your experiment, you actually want to set your retention time so that the K prime would come out about 2. So keep that in mind. That's when you actually get a pretty nice resolution, right? So, I mean, typically, right, K prime of about 1 through about 10, right, range give reasonably okay selectivity. So even if they're resolved, right? Because I mean, this is there's not much overlap. I mean, there's overlap. So there's a band here, there's a band here. So there's not much overlap, right? So again, these are still resolved, but the resolution, this one's higher, has higher resolution, right? Because it has higher efficiency. So the optimal comes out around 2. So you want to change your setting, the retention time. Right, and I'll actually show you a little bit of an example. Pictorially speaking, let's say if K prime is, well, let's see. I'd like you to draw this, right? So let's see. I'd like you to draw a couple of peaks. Peak 1, and then peak like this. So basically, so if K prime is equal to 0, and K prime is equal to 1, K prime is equal to 3, K prime is equal to 5, K prime is equal to 8, 4, and alpha in this case is 1.1, and n is equal to 1600. So, I mean, if you just plug in numbers and if you try to calculate the resolution, that's what you get. Anyways, my point is that, depending on what, you can still resolve, again, if efficiency is not, it's a trade-off between where the peak actually happens, right? Where the peak happens and how efficient it is. Right? So sometimes you do have to make your retention time to be really far apart, right? So keep that in mind. I'm going to actually give you a little bit of example. This is in your textbook, I think. This is the next chapter, but I'll just use this as an example. Are you going to see Megan today?
I will tomorrow.
You will tomorrow. Okay, then I'll give this to you, but I'll also put this up on Sakai as well. Right. So, anyways, basically what you're looking at is this is a temperature control. So basically, the first figure, you can see that it's not really well resolved if you look at figure B, right? I mean, you have multiple peaks. There are supposed to be a total of 9 peaks, but if you look at the first 4, it's sort of buried in the figure B right here, right? So it's not really resolved well. The way this system was handled was that you change the actual flow rate, you change the temperature, right? And that will affect the column efficiency. But anyways, So this one had a temperature gain of, I think, 30 degrees per, I think, minute or per 5 minutes or so, I don't remember. Yeah, 5 minutes, 30 degrees per 5 minutes. So then the mobile phase, right? Well, in this case, the temperature is affected, so the migration velocity changes, so retention time changes, and then you can resolve. So again, so the retention time changes and then resolution changes. That's basically what I was basically telling you, right? And there are number of ways to do to change the retention time. The changing temperature is one of them. Also, you can do programmable flow rate speed as well. The HPLC, for example, you can change the flow rate, and also you can change. And when we talk about HPLC chapter, we're going to talk about the solvent change. Basically, instead of using 10% methanol at a certain change, the gradient changes from 10% as time passes by, going from 10% to 50% methanol. So again, there's a concentration gradient change that would affect the interaction between the solute to the stationary phase, right? So HPLC, remember, HPLC, there are 4 bottles, like methanol, ethanol, acetylnitrile, something there. So again, that you can change the mobile phase, and that will affect the retention time, right? And then you can change, once you change the retention time, you can actually solve. And that's all it is, basically. So keep that in mind, right? So that concludes, this concludes the chapter 26. We covered all the theory, somewhat, all right? So, so that is the part for the quiz for Thursday next week. So it's like, whoa, yeah, more than a week. Should I do the quiz next Tuesday instead?
Oh, preferably not.
So anyways, if you'd like to take a quiz earlier, you can, all right?
Okay.
Just let me know, all right?
Yeah, Megan and I have to give seminar presentations on Wednesday.
Wednesday?
So.
Well, which means you better actually, so by the way, keep that in mind, it's a quiz, it's not a test.
Yeah.
So you don't want to wait until the day before. I mean, study a little bit every day, right? Those problem sets, all right? So now, okay. So far so good? All right. Now, let's see. All right. Then, what else? Detector. I do a detector. How much time did I spend so far? 10 minutes, 20 minutes?
1:30.
1:30?
It's just
Let me actually see the syllabus, because actually I did allocate 1 extra day. So I put detector on September 12th. It doesn't say it on your stuff. If I do detector, the test is 17th. We can still do detector on 19th. I think we are in good shape. So I'll just cut it today, short. Is that okay?
Yeah,
And I'll answer. So I'll stop the video and I'll answer your question.
Okay.
All right?
It's just a really quick question. I'm just hung up on what you use or how you manipulate something.
But today's homework, I'd like you to do it today. The problem set number 2. All right?